Well, welcome back to our classes. It's this here is the sixth class, and we're talking about nuclear models. In fact, just a quick intro: nuclear models are, and nuclear structure in general, very what how could I say? It's a very advanced topic. It wouldn't really fit a deep discussion of it wouldn't fit in this course. But as it's in the program, we'll try to give just a glimpse to understand why do we need models, what models can do, and the essential families of models, right? Of course, as an advanced topic, this shouldn't be part of the tests and anything. It's just for general knowledge. So, why do we need models? Well, nuclei are complex systems with many bodies involved, just as atoms, in fact. But the main difference between nuclei and atoms, in atoms we do understand the interaction involved. It's the electromagnetic interaction, so can do a lot of calculations. But we still need models because systems are too complex for an exact solution to be found. In nuclei, things get worse because we do not understand completely what the nuclear interaction is. We have ideas, we have some models, and we know it's a very complicated thing. So, okay, if we want to understand how the nucleus is inside, we do need to do models. And what are these models? They are essentially simplifications that are made for, first of all, understanding and explaining phenomena, trying to figure out how the nucleus is inside, how it works, and the reasons for many things we do observe. Right, for instance, why some decays are more probable than others, why some structures are more solid than others. For instance, why helium 4 is such a bound nucleus and beryllium 8, which should have 4 protons and 4 neutrons, is not bound at all. So, how come? Right? Models can do that for you. Understand fission, understand fusion processes. And this also allows calculations of structure properties and decays. And that can be important if you want to understand some nuclear properties and predict nuclear properties for nuclei that are hard to observe, but they may be important. For instance, when we talk about how the heavier elements were produced in a supernova explosion, we have to assume we would, for a complete calculation, we would have to know properties of several nuclei on the heavier side, but they are far from the stability, meaning they last too little and they are very hard to produce in an environment that's not a supernova. Just to make clear, supernovas have a rich abundance of neutrons, high energy neutrons. So many reactions happen that we cannot really replicate on Earth. And so we have to have at least the idea of how long do they last, their half-lives, and how often are they created, meaning the cross sections involved. So we need models, right? And essentially there are two families of models. One is the family we call the collective, which is collective models. We're talking about the nucleus as a whole, as opposed to trying to understand the properties of the nucleus by looking at the odd particles. Let me just give you an example. The most famous and probably first nuclear model was the liquid drop model. It's a collective model in the sense that it treats the nucleus as a whole, as if it was a liquid drop, really. And so we have a surface energy, which is negative. We have a Coulomb energy, which is negative too. It's the repulsion, right? And we have the volume energy, which is positive. And then when you sum them all up, we come to that thing we already know from before, the binding energy per nucleon, and we can reproduce really the general trend of the curve is clearly reproduced by a simple model that could be easy to, if I wanted, I could present you and you could do this calculation. Just don't see much point in it, but just for you to know, okay, very simple things. We can, just assuming it's similar to a liquid drop, right? It also explains nuclear radius. It's good to explain some cross-sections, general cross-section ideas. It's good to explain fission, for instance. You can understand, think of fission, think when you have a liquid drop coming through your window. Small droplets, they tend to join. It's much similar to this one, right? Small droplets tend to join and form a larger drop, and once a drop is too big, the chance that it will break into increases, right? And that's what we see here. This is a very simple, one of the first models of the nuclear fission, right? A neutron goes on a spherical neutron, it gets distorted, and then it ends up divided into smaller droplets. Okay, just an idea. There are more complicated collective models, but they all try to do the same thing, explain the properties of the nucleus as the properties of the nucleus as a whole. The opposed idea is the shell model. Shell model, think of the nucleus. They are more refined. At one hand, they are more refined models, right? What they do essentially, they think of the nucleus as we think of electrons in an atom. But now remember, the interaction is not so well understood. So we think, okay, if for 4 electrons in an atom we have several orbits where they can, right, quantum mechanically speaking, there are stable orbits around the atom for the electrons. The same should go for nucleus, right? With a different small tweak here. Well, when we think of Pauli's exclusion law, it says you cannot have 2 identical particles with all quantum numbers equal. That's what makes the shell model work, right? So you have 2 electrons on the first one, then it doesn't fit another electron, you have to go to the next level, and so on. For nuclei, we have to remember that neutrons and protons are different particles, so you have 2 sets of states of levels, one for the protons and one for the neutrons. You can have on the first shell 2 protons, and on the first shell 2 neutrons also, because they are different particles. So okay, what happens then? What can we explain using a shell model, right? Remember about for electrons we had the magic numbers, which essentially explain the noble gases, right? When you have a closed shell, it's very hard either to take 1 electron out or to put 1 extra electron in, because shells are all closed. That's essentially what happens in nuclei too. So if we take a look, you see that, for instance, here with 50 protons you have several stable nuclei with 50 protons. Same goes here for 82 protons. And the same thing happens for neutrons, for instance, 82 neutrons, 50 neutrons. So we do have, for some, we have a clear impression that some numbers for neutrons or protons are favored against others. And that has to do with closed shells, just as in electrons, right? So it's a shell model. You have shells, you fill the shells, and all of a sudden they are closed. and that explains things like quadrupole moment and all that, right? One thing is that now, as we have the neutron, here we have this here, all this excited states, for instance, but we start to mix neutron states and proton states. They try to explain the nucleus as you have a closed shell, which is a double magic number nucleus, and then you have the particles that are outside this. So if you have, I don't know, 50 protons and 82 neutrons, you have a double magic. Then you have extra particles. They will start to pile up here, and then these extra particles will explain all the characteristics of the nucleus. That's essentially why they are called single particle models. These extra particles will explain, and in more complicated issues we get the largest even nucleus we can, and just think of the particle that's the particle or particles. You can have one proton, one even is you have even number of protons and an even number of neutrons, and you say, oh, these are all coupled, and we now have an extra particle here that could be a proton, a neutron, or a neutron and a proton, and these will give most of the, at least the lowest energies states of this nucleus. So that's essentially how a shell model goes. Of course, there's several complications here, because if you're not in a double magic nucleus, then you have to understand the shape of the nucleus. It may be distorted by forces and everything. So it's much more complicated than this, but this is the general idea, right? And that's it. Models. So this was just a very quick introduction, just to give you an idea what the nucleus is inside. Just taking a look here at this excited states, we can explain some things. For instance, we can explain, when we talk nuclear reactions next, we'll talk about resonances. They have to do with this. When we talk about gamma radiations, they have to do with this, and so on. So that's just a quick intro on nuclei. Okay, see you next time. Bye bye.